Okay, thanks a lot. Yeah, so I'm going to give a talk today. It's definitely from the perspective of somebody who's got a background in PDEs and analysis and scientific computing. Part of it will just be a general introduction for those of you who are less familiar with machine learning, and then a little bit of a comparison between traditional machine learning, deep learning. And then eventually I want to cover some of the generalization theory, going through the standard material. That'll be more of a blackboard proof. But the reason I'm looking at it is because I want to look at it from a slightly different point of view. And that's from the point of view of somebody who's interested, well, our background, PDE and regularization. So rather than focusing more on the algorithms, which is how the CS textbooks and articles do, I want to focus on what are the properties of these solutions, which is what generalization theory already does, but there's a small extra ingredient, so we'll get to that later. Okay, so I'm starting with the boring slide before we get to the exciting slide, which is traditional machine learning. What's different about it? Traditional machine learning is a big field. I didn't see a big connection between that and our research area. So you see, I have a couple problems out here. Spam detection, that's classification, and it basically uses Bayes' theorem, right? You look at a bunch of messages, you know if they're spam or not. What's the probability that a certain word, say inheritance, is a spam or not? And then you use Bayes' rule to flip it around and classify something as spam or not. And notice that along with the classification comes a probability. So it's outputting spam or not, and also a probability. Well, actually, it's starting with a probability, and then you threshold to decide whether to classify it as spam. Something else, clustering k-means. Again, this is a very simple algorithm. Mathematically, it's not worth studying. Well, no, I shouldn't say that at all. It's a non-convex problem, so we don't have the kind of analysis we have for convex optimization that lets us sort of generalize this algorithm, although there's plenty of great work on it, and other types of things. But what I want to emphasize is we're close to statistics, we're close to sampling, and I'll show essentially an inequality later that says if you have a survey, you survey a bunch of people and ask what they're going to do in the future, in the next election or whatever, with that survey comes a probability. So I don't just say, 65% of the people are going to vote for this proposition. I say that's correct within a certain tolerance of 5%, 19 times out of 20. And in a similar way, machine learning results, which come with a prediction, it also comes with a guarantee that this prediction will be correct. My error will be within 5%, 19 times out of 20. Now, that's something we don't have for deep learning. In addition, it's interpretable. If I tell you your message is spam, you can go back and say how I decided, which words mattered. Okay, now we have the super cool deep learning stuff, right? It's way better, but all that goes out the window. What we have instead is one thing, accuracy, super high accuracy, or performance, super good performance. So we have natural language, I said classification, that's not right. We have games, reinforcement learning, generative models, deep fakes. All this stuff is really amazing, but we've lost the foundations of traditional machine learning. So the question I'm interested in really is how much of what we had for traditional machine learning can be brought into deep learning. Okay, and it's all over the place. If you're not paying attention, and we know it's in medicine, we know it's in commerce, it's in banking. I had students do an internship at a bank, and so I found this slide online for people are using it all over the place, and they're replacing their traditional machine learning methods with deep learning, sometimes even when they don't need to. Okay, so now let me focus in. I don't know, away from those other topics like reinforcement learning or natural language processing, and just get into image classification. This seems like a natural place to start because unlike a lot of other machine learning problems where your data might be a database, we have images, right? And images are living in well, we would say they're functions, right? Functions on a 2x2 rectangle. And computer scientists would say, well, this guy's living in R36 and this guy's living in R256. It's a different point of view. Anyway, so image classification maps an image to words, basically. And it's super effective. The sort of baby data sets that go back to Jan LeCun doing automatic check processing is MNIST, right? And it's a pretty simple data set. Even there, though, the dimension is 28 squared, which is big if you think of it that way. And people have developed other sort of baby data sets like Fashion MNIST, which is black and white and pretty small, but you can tell that it's different types of close. The one that's sort of the main one we study now, which is big, is ImageNet. ImageNet, this is just a tiny subclass of ImageNet with some birds in it, but there's 20,000 different classes, and there's 14 million images, and the dimension of most of them is 256 squared times 3 color channels, so about 200,000. Okay, now this slide's a little old, but it used to be, about a year ago, it was a lot of work to train ImageNet. It took 256 GPUs. Now you can do it, an academic can do it. So you can buy a 4 GPU system and train it overnight. And that was, well, Chris can tell you about that. That was mainly just doing some smart stuff to speed it up. I think the biggest thing that they did to speed it up was to start with coarser images and train on coarse images, and then only deal with full resolution as needed. Okay, so, well, it's an amazing thing that we can classify these images so well. And here's one example that got me interested in this problem really quickly, is that the classification, so the neural networks that classify with super high accuracy are also vulnerable to an adversarial attack. So let me preface this by saying that if you add random noise of this tiny amplitude to an image, it doesn't confuse the network. So you can take many, many random noise vectors and it'll still classify this as a panda. But if you dig into the network and search for a small adversarial perturbation by doing optimization, then you can find a tiny imperceptible image which will cause misclassification. And you can do this consistently across all neural networks and all images, basically. Some might be bigger than others, but it's a real problem. It's not as big as a problem as I thought when I originally saw this example, because remember, all the theory is saying you're doing things in expectation, right? You're training in expectation. And in fact, the most certified defense to this problem is actually to add noise to your images, evaluate it a lot of times, and then take the average of the predictions. So you get around this adversarial attack essentially by doing what you did during training, which was show lots of different slightly perturbed versions of the image and see what the prediction is. Okay, in fact, the real point I'm trying to make is this. Nobody says that when I train a neural network and I get 96% accuracy, that if you give me one image, I'm going to be right. It says that on average, I'll be right 96% of the time. So it's a slightly different thing. Okay, so let me now slow it down a little bit and just set up our notation for classification. So the first thing that's very different about what we're doing, although we're not going to use this fact, is that we're going to assume our data set, it's not spam, it's not emails, it's actually an image in 0, 1 to the d. Okay. And we have labels, k labels. K can be 10 if it's MNIST, or it can be 20,000 if it's ImageNet. And then this is the standard notation. You have a data set S with M samples in it. They're pairs of images and labels. And that's what you train with. Okay, and the assumption we make, the theoretical assumption we make, is that these samples are drawn IID from some underlying but unknown distribution. Okay, so there's some row of X that's generating these images. We don't talk too much about that, and most of the guarantees are distribution independent. So the proofs you do will work for any row. Okay, and you're given these labels, and then the important thing is this: you have a loss function. And the loss function in machine learning is kind of a funny thing, because when you're doing classification, what you care about is the 0-1 loss. Are you right or are you wrong? But when you're doing the training, you replace that with a surrogate loss, which is continuous at least, and sometimes convex. So let me draw that. So usually our models don't output, let's say it's binary classification. So if your output is supposed to be -1 or +1, then you've got some function, say h of x, which could be a number, and then you're going to classify with the sign of h of x. Okay, it could be 0, but it's basically in -1 or +1. So that I like to write this as the classification of x. Okay, so now when you train, your loss that you actually care about is that if this is your value h, and let's say that y is equal to +1, then you're happy here, so your loss is 0, and you're unhappy here, so your loss is 1. Right or wrong? Okay? Now, what you actually do, so this is the 0-1 loss, but the simplest thing to do is actually train with a loss like this, which is called the hinge. Now, what you have here is some margin rho where even if h is 0.1, even if you're classifying correctly, you're going to pay a small price for that. Okay, you're going to have a little bit of loss because it's not confident. Any h greater than rho is 0 loss. So you've now introduced a margin to your classifier. And it doesn't matter too much. If you want, you can chop this off and make it 1 over here. Then it's non-convex. You don't get these big numbers. But in practice, when the classifiers are good, everything lands around here anyway, so you can have this convex loss. Okay, now the margin is something quite important for regularization. And we'll talk about that later. Okay, so here's the setup. They always assume, I was talking to Jeff about this yesterday, it's kind of weird. If you're solving a PDE or an image processing problem, you don't just, what you prove is that you get to the solution. Okay? But in the generalization theory, they don't do that. They assume that you're going to train a model that's really accurate anyways, and they just prove the generalization gap is small. Okay, so what you see here is, what you care about is the expected loss on new images. Okay, that's some number. We hope it's small. But all we know is, let's say, the training loss. But if this training loss is not to our satisfaction, then we just throw it away. We throw the function away. So we're not focusing on showing that we can make this small. Now, the other thing about this is, in practice, what we do is we reserve a holdout set and estimate this empirically on some data that the model didn't see.
Is this the function
F is the function that I'm going to train. F.
So usually they don't want to get the F that minimizes this thing.
No. So that we're completely separating training from generalization. So we're going to find the F, we're going to do training, which is minimizing a loss function. So we're going to minimize this, usually, to train. You minimize your empirical loss over the data that you can see, and then you ask the question. So overfitting would be, I get 0 empirical loss, I classify everything perfectly, but you know it's oscillating like this. And now when I show a new image, I'm just always wrong, or wrong with high probability. So they're trying to deal with the gap between your training loss, which you made small, and your generalization. Well, the theory, I haven't even gotten to that yet. That'll be on the next slide.
No, you wrote that instead of minimizing the empirical loss.
We're going to minimize this over a class of functions, over f in some hypothesis space. And then so one thread will be to show how do we do this and can we get it to a small loss. And another somewhat independent thread of the theory will be to show that if you did this, under what conditions on the hypothesis space is this number close to this number. And that'll be two separate parts, actually two parts of the tutorial. Okay, so here we go. This is the losses that I was kind of talking about. Now, if you don't, your first pass through, if you don't like these classification losses, you can just pretend we're doing regression and the loss is just quadratic. It doesn't change much for the theory we're doing. The theory of generalization doesn't care much about the loss, really.
So generalizing, minimizing that abstract thing with the probability
Yeah,
density?
basically, yeah. Okay, so there's the 0, 1 loss. Now, I was thrown off by this for a long time. Most of the textbooks just deal with this binary classification. And to make the notation simpler, they just multiply yi times, h of x, and just look at the sign of that. This is just like a notational trick, and that's your loss. Because, well, if they're the same sign, I'm happy. If they're opposite signs, it's bad. So I could maybe say 1 minus this. It'll be 0 now if they agree. And it'll be 2 if they disagree. So that's my loss. So you'll see this formula. I don't love it because it's just a notational trick for binary classification. For multi-classification, there's more than one way to do it, but the most popular thing, which looks weird at first, is for each class you train a function. So you have 10 classes, your output is a vector, and it's called a scoring function. And then you just look at the highest score, and that's your classification. Okay? So I have 10 functions, and if function 3 has the biggest number, that's my classifier. And so there, you might look at the gap between the biggest guy and the correct guy as your loss. Okay? But like I said, we can just pretend we're doing regression. Okay, now I want to get to the hypothesis classes. This is where things get really funny, okay? Because this is a completely abstract thing, and generalization theory is going to prove something about this H. Now, I taught statistical learning theory last fall, and they take so many steps to get to the interesting part. Okay, they start with I have something super discrete, right? You have a string of truth statement, not x1 and x2 and not x3, and how are we going to learn that? Okay, it's very discrete, and then they go through VC dimension, which is what most of the computer scientists know. They talk about that a lot. And they prove things like, okay, if my data set, this is sort of chapter 0 or introduction or chapter 1. If I'm trying to find, a good pineapple, and this is, how heavy it is, and this is its skin color, and I want to classify good pineapples by these two qualities, how do I learn this rectangle? Okay, super simple stuff, learning a 2D rectangle. And eventually you can prove directly that a simple algorithm that takes either the smallest rectangle or the biggest one, or if you want the average one, will generalize. That's assuming that your data is drawn from this kind of thing. And they build their way up to VC dimension. And one of the main results of VC dimension is to show that if I do linear classification, so essentially, if my hypothesis space, so f of xw, is just x times w. Okay? If it's linear, then they show that essentially you can do the VC, so this is my h. Then they measure the VC dimension of h, and that gives you some control on generalization error. Okay, but the problem with this is that the estimates you get depend on the dimension. So if you're in dimension 100 or dimension 1,000, your generalization error gets worse. And what we really want is dimension independent bounds. I don't want to double, the resolution of my image and get a worse bound on it. It's basically the same image. So for that, it's Rademacher complexity. And so I'm going to try and skip straight ahead to this type of complexity. And the reference for all this is a textbook by Mowry. Okay, and he does that in chapter 3. Most other books just put it at the end of the book. Okay, so here it is. This is okay. This thing is not a good classifier. If I choose any linear function to classify, I can overfit. And you can see it from this picture. If I'm doing binary classification in the plane. I've got the circles and the dark circles. I can fit it with this plane. I can fit it with this plane. And if there's not a lot of data, I could fit it with this plane, right? Which is probably the wrong plane. But there's nothing in my fit. My loss is 0 if I use this plane. And that's why this won't generalize. As I sample more and more points, I'm going to have to choose a plane that probably fits in there. Okay? So you can do that fitting. Your bounds are worse. The way to get dimension-independent bounds is to add a penalty for the margin. So to penalize, you want this to maximize this distance. Okay, and that's a really simple thing. And what pops out, if you use a simple formula from geometry, well, actually it takes a couple lines, but basically the margin is proportional to 1 over W. Okay, so then I might have wrote, no, this is right. So maximizing this is the same as minimizing this, and this is what pops out. Yeah?
So when you say dimension-independent generalization bound,
Yeah.
could you say what that is? Is that abstracting bounded in terms of the
It's if x is in Rd, then it's this D. So if my data is 1 or 2 dimensional, fine, it doesn't really matter. But we want to deal with data that's in 1,000 dimensions. And so if I'm doing linear classification in 1,000 dimensions or in 1 dimension, I want a theorem that says I get a bound that doesn't depend on the dimension. Because I'll get to this later, but basically, actually, this is an important point.
But a bound on what? Could you write what it looks like?
Yeah, I'll get to that. I'll get to that in a sec. The reason we're doing machine learning instead of just function approximation, right? We have beautiful results in function approximation, but they almost all use grids or Fourier or something like that. And even though the bounds you get are exponential in the number of points, they depend on, it's the curse of dimensionality. They depend on the dimension of the underlying data x. And the point of this is to get dimension-independent bounds, which I can skip ahead to it in a second if you want. Okay, let's go back. Okay, so I just want to make this point, which is when they do this loss, so you don't just minimize the loss, you add this term. Well, in this case, that's the gradient in x of f. So now it looks like we're doing Tikhonov regularization. So it made me wonder if this type of regularization might be somehow the key to generalization, or some type of function regularization. This is just an algebraic trick because it's a linear function. But now when you jump, and by the way, this is the image. This is Wikipedia machine learning. This is the sort of icon of machine learning. And this is the classic picture of kernel methods. So kernel methods were a big deal because they let you lift your data into some abstract feature space, which can be even higher dimensional. So I can have way more features than the dimension of my data, and then do some kind of classification that picks out the important ones. And the way they talk about that is, it's a funny picture. You've got your data lying, this is the underlying data space where it's not linearly separable, but I could lift it up with a function into, now this is a higher dimensional space, even though it still looks like the plane. In some higher dimensional space, now it's linearly separable. And they give a couple examples of how you could actually do it. Some, like maybe the Swiss roll or whatever, you could lift it into higher dimensional space, it's linearly separable. Fine, but that's not a true story. Okay, that's like a metaphor for what they're doing, but it's not actually what they're doing because you can't use any functions to lift it up. You can't make up any features. There's a whole bunch of heavy math of reproducing kernel Hilbert spaces, which is the only time you're allowed to do this. And now, and actually most of the textbooks even have typos in what they write, right? Somebody, right? Most of them they write the Hilbert space norm of the weights, which doesn't make sense, because weights are parameters, and it's the functions that matter. And so when you dig into it, this is actually, when you go to kernels, now you have your functions. This is the regularization where this is the norm in a reproducing kernel Hilbert space. And I'm just throwing it out there to show that the only other example we know where we have these bounds also has some function regularization. And I'll give some examples of this in the next couple slides. The other funny thing about this is if you do Fourier analysis, are you saying that you're lifting a function into a higher dimensional space and then finding an affine approximation in that space? No. The way we learn about expansions is we would just say, I start with some nonlinear function f of x, and I take a series wi phi I of x. Okay, kernel methods are kind of doing this, or basically doing this, but they're saying they're lifting it into a higher dimensional space. I would just say you're finding a nonlinear function with a linear expansion. Okay, so I'm excited about this, but I don't want to oversell it because this is just a point of view. It hasn't solved any problems yet. I'm just hoping that it'll inspire me or some of you to use this perspective to deal with the deep learning stuff. Okay, so here's a little more details on the kernel method. So this is the hypothesis space now, where this phi is a vector. Well, each of these is a single function, but you write capital Phi for the vector of the entire sequence of these functions. And the kernel trick, which is important for the algorithms, but less so for the theory, is that you can do a giant dot product, which would otherwise be way too costly, and evaluate it as this function, this known function that just depends on x and y. Let me just give an example of that, because I was putting this up there just to sort of get it out there. But the most common example is for k of xy could be, the exponential of x minus y squared. Okay, and then that kernel map, it takes some time to show this, but the kernel map would be to put a little Gaussian unnormalized at x, put another Gaussian at y, and then k of xy, this function, you can write it as the dot product of these functions, integrated. Okay, so that's just an example, but usually you have some formula. And kernel methods, there'll be a lot of people, I think, talking about it in our second workshop. They have great math, but people did a lot of work to push them as far as they could, because what ends up being hard is choosing your kernel. Okay, you have to choose the kernel that you want to do all this fitting with, but you don't have so much freedom to do that. And so people worked hard to really milk this for as much as they could. Okay, so let me just give some examples here. If you look in the books, and this was actually beautiful math from like decades ago that was brought back to life by machine learning. But the early examples were low dimensional, and they gave you Fourier type regularization. And so if you dig around, you see that here's some examples. So for the Gaussian kernel, which is a popular one, the regularization you get is something in Fourier. You transform your function into Fourier space, and you have a multiplier by a Gaussian. So that's really strong smoothing. And you can also rewrite that if you want to write it in the original space, not Fourier space. It's like all derivatives. I'm penalizing all derivatives of f. Okay, with a coefficient, like that decays very fast. Okay, so that's super strong smoothing. Yeah?
So usually when I want to minimize the function,
Yeah?
and so I don't have enough compartments, then I add a higher derivative order.
Yeah.
In that group based within the compartment. But here we are in a finite dimensional setting.
Yeah.
Okay. So why do we regularize?
So that's a good question. So okay, another way of looking at this, let me just say not from the point of view of function fitting, is I have a bunch of samples here and here. And what I'm doing is, and I have labels, so it might be +1 here and +1 here. But somewhere else, my function might be -1 if it's binary. So this type of machine learning is just saying I'm going to add a fat Gaussian it's like radial basis functions. I'm going to add a fat Gaussian at each data point. And if I sample enough, hopefully, it'll give me the right value here. That's basically what it's doing. So I'm fitting by expanding in these functions. Now, does that generalize or not? I'll tell a bit of the story of that. But to directly answer the question in terms of regularization is the goal, but it's not something that I've found in the literature. It's more that they have this algorithmic way to get some generalization, and then we can interpret it as regularization.
So later you want lambda small?
Yeah, you want lambda small, yeah. Or you tune it. You can always tune lambda. Okay, so then this is what you see more in the books is, okay, if we're doing kernel, and it's with the quadratic loss, then you sort of go through these steps and you end up solving this problem, solving a regularized least squares problem with a symmetric matrix. And the matrix is the Gram matrix that comes from the kernel coefficients, k of xi, xj. Okay, so algorithmically, which is more the focus of what you see, we're going to care more about finding the weights, right? So if these are my labels, it doesn't mean I'm going to put one here and one here for my weights, right? You solve a linear system to find the best weights that give you the best fit. Okay, so this is the focus, finding the weights. You see the regularization without lambda, you're solving a linear system that may not be well conditioned. Adding lambda gives you good conditioning. So it's pretty clear what's happening in this perspective. The previous slide was translating it back over to the function rather than the weights. Okay, so the function, I just erased it. This is the function. Okay, so the point is, unlike, there's nothing orthogonal about this expansion, so these are full matrices. And one of the reasons that kernel methods sort of started petering out a little bit is that for really large data sets, you can't even solve a linear system with a non-sparse matrix. You can't do 10 million times 10 million. So people got around that by maybe doing SGD for this system, but still it was starting to push the limits. Okay, so just to summarize this part, maybe we can learn something by using, so essentially what I tried to sit down and do is redo the proofs of generalization using this perspective on the functions rather than looking at the usual way. And I hope it's a fruitful thing. And in particular, when you do this, can you look at the proofs and now do non-parametric generalization proofs, which would perhaps apply to deep neural networks? So the point there is, as a first approximation, say, look, these deep neural networks can essentially fit anything. So let's just pretend we're just dealing with functions. And if we added some regularization, maybe that would give a generalization proof. That immediately would if you could do this type of regularization. But there's a problem here. We can't evaluate any of these norms in high dimensions. We can't literally sum this gradient of x everywhere in a high dimensional space, so you have to have an indirect way to do the regularization. Does that make sense? Okay, so here now is statistical learning theory. It's all about overcoming the curse of dimensionality. So if you look at this and you say to yourself, oh man, I mean, we can do so much better with Fourier or whatever. Why are we bothering? We're bothering because we want to get around the curse of dimensionality. Okay, and this is the textbook that I like, and you can get the PDF for free from the author online on his webpage. Okay, so here's the curse of dimensionality. So if you look in approximation theory, the problem you have is all your error estimates for approximating a function depend on the spacing, essentially. The grid spacing. And the grid spacing, the number of samples you need to make this small goes like 1 over square root of d. So in high dimensions, to get a box of a certain width, I need exponentially more samples. And so the bounds you get become vacuous. Okay? The h that you get is basically 1, really 0.99999, so you don't have any good bounds. Okay. Okay, so the bounds we want it to depend on m, the number of samples, but not d, the underlying dimension. So okay, so again, I'm not going to do any regularization. What I'm going to do next is to go over how Rademacher complexity gives you generalization bounds for support vector machines. I'm going to do that on the blackboard. The step from here to here for kernels is almost the exact same proof, but instead of a dot product in Rn, it's a dot product in some Hilbert space. Everything's the same, but I won't do that proof. And then this stuff is just sort of speculative. Is can we take this theory, or can you guys this semester take this theory and find a way to give a proof for general function approximation that's not written in this particular way? All right, so before, I got 2 slides before the blackboard proof. So earlier I said, look, the bounds you get from statistical learning theory are almost the same as bounds from sampling theory. So what are the sampling theory bounds? We're literally talking about a coin toss. You flip a coin, right? SM, the sample mean, is the average number of heads. Okay? And so there's the true probability of heads and the sample mean that we care about. And we know that roughly the error that I get should be like 1 over square root of m. That's the sort of central limit theorem version. Central limit theorem tells you these things converge in the limit, but doesn't give you, for fixed m, a bound on your error. Right? I know that I'm converging to a Gaussian, I know the mean and variance, but it doesn't tell me for finite m what the error is. And so the concentration of measure, and Jeff Calder will be going over these inequalities as part of his talks, they just give you the non-asymptotic version of that. So if I'm tossing my heads, the probability that I'm off by more than epsilon is bounded by this quantity. It's exponentially small in m, and there you go. Okay, this is the concentration of measure inequality that you can prove. And when you sort of solve for delta, so you set delta to be the right-hand side, solve for epsilon, it translates to this. Okay? So it translates to your error is less than essentially this factor over square root of m with probability at least 1 minus delta. Okay, so that's what you get for flipping a coin. All right? So now if instead of flipping a coin, you're trying to learn a function and you're trying to show that the empirical average is close to its true expectation, we're going to see exactly this type of formula, exactly this expression, but there's going to be one extra term. And that one extra term is the Rademacher complexity. Okay? Okay, so there it is. So the gap for learning has this log 1 over delta over square root of m with probability 1 minus delta. And the only extra price you pay is this. So if it's 0.02 is the Rademacher complexity of my space, then I get an extra error of 0.02. Okay, I didn't tell you what the gap is yet, but I just wanted to emphasize that it's a very similar type of thing. So learning bounds are like sampling bounds plus Rademacher complexity. Okay, so what are they? So this gap is the difference between your empirical mean of f. I'm going to write this down on the chalkboard anyways, and the actual expectation of f. And the proof we're going to do is just to bound it uniformly over all functions in our hypothesis space. That's the idea. Okay, are we ready for? So I've been talking for 45 minutes now. I have half an hour left, so I'm going to switch gears and try to prove, 6 pages of stuff on the blackboard. Does that sound good? Yeah? Good. Now I have to work. Okay, so sort of step 0, page 0, is concentration of measure. Okay, so the first inequality, which I'm pretty sure Jeff cover, is this one. So I take m random variables, IID, and they take values, bounded values. Okay, I'm going to average them. I'm going to call the average, I'm going to call all of them my sample. And I'm going to define this function to be the average. Okay? And now I want to ask the question of what is the gap between f of s and the expected value over all the samples of f of s. And this is just the expectation of f, because it's just an expectation of an average. All right? So writing it this way, Hoffding's inequality says that the probability that this is bigger than epsilon is bounded by this exponential. Okay, and if you see this b minus a, well, there's something going on with the m and the b minus a. So I'm just stating this to use later. Okay, the one we're going to actually use generalizes this. So everything is the same here with my samples. But now instead of that f, I'm going to take a more general f. What's my f going to be? It's going to satisfy the following. If I take my original sample and I just tweak it by resampling so I just changed one value by sampling it over again. Okay. Now, every time I do that, what I want is this f to satisfy that changing one value doesn't change f very much. Okay? I change one value, I still get this 1 over m, okay, and this factor. So that guy should satisfy this.
Kind of a Lipschitz spell, right?
Yeah, kind of. It's like an average, basically. That's all I need. Well, if I assume this, then literally the exact same inequality holds for that. So it doesn't have to be a linear average. It's anything that satisfies this tweak.
Same concept.
Everything's the same. Okay? So that's great, because this is the type of f's we're going to be working with to prove stuff.
How many xi primes can you take? Just one, or can you change?
I'm just changing one at a time. I mean, probably you could change 2 and see what the condition is, but we don't need to.
How about square root?
Yeah. Okay, but that's what we're going to use. You'll see that it holds for the functions we want. And then so sometimes we like to write it this way. Sometimes we want to do the thing I talked about on the slide where we solve for delta.
Do you have it square or why square?
Yeah. I think maybe because there's a square. I don't really know. Yeah, I think maybe the squares.
You can do it direct. F is in that.
You don't need the square here, I agree.
No, this is the same f or a different f?
No, I was calling this guy f
Yes.
just to emphasize that when we generalize to any f that satisfies this condition,
Okay.
the same inequality holds.
And it should be probably the same.
It should be what?
There shouldn't be no square, I imagine, right? So you're just changing one.
I don't know. Jeff will.
I think it shouldn't be a square.
No square? It's just b minus a. Okay, that looks right to me too. Like that?
Yeah, this is what we generalized it.
Okay. All right. Okay. So the last thing, so we're going to use this. The last thing to check is that if you set this equal to delta, if you call this right-hand side delta, then what you get for epsilon is this. You get that. Okay? And so that's what appears in the other way of writing this bound with probability 1 minus delta. Okay, so that's the only concentration of measure we're going to need. Now I want to define the complexity. Okay, so I've got my hypothesis space of functions. They don't have to be parameterized by W, but just to make it a little less abstract, think of them as some set of functions, maybe parameterized by W. And for later, the example we're going to have would be under the condition of a bound on the norm of W, and that we have a bound on that all your data has a bound to. So this is the SVM setting where we're going to use Rademacher complexity. But now, for now, it's completely abstract. Okay, but then we also have a loss. And we're going to maybe prove things about the combination, the composition of the functions with your loss. So they take a pair so we might prove things about the complexity of G. Okay, now let me define it. So X is our data. Y is our labels. And we'll call the whole thing Z. So it's a bit weird. We're not just proving things about the complexity of our functions. It's the functions composed with the loss. But at the end of the day, this Z could just be abstract. And it's not a big deal going from one to the other. So here's the definition of the empirical Rademacher complexity. So you've got your G, you've got your S set of samples. Okay, so it's the fanciest letter I can write down. So the empirical Rademacher complexity on the sample S is given by this formula. Okay, it's a formula. What does it mean? These sigmas So sigma is a vector of Rademacher variables which are +1 or -1. IID, obviously. So they have probability 1/2 of being +1 or -1. And I'm basically saying I have, well, one interpretation of this is that you have a vector, a random vector of +1s or -1s. And how well over my whole function class can I correlate with that vector? Okay? So it's almost saying, can I fit random noise? If I can fit random noise, that's not so good for complexity. But if my functions have a hard time fitting random labels, that's low complexity. Okay, but that's a definition. We're going to be able to zoom fairly quickly from that definition to what we want. Okay, but there's a little extension. There's the empirical one, which is one version of it, and then there's the non-empirical one. Which is just depends on the number of points, not the sample. So now you just take expectations of the empirical Rademacher complexity, which depends on your sample of size m, over all different ways of drawing a sample of size m. Okay, so now can I get fancy with this? Okay, so let me write the theorem. Okay, so we're going to specialize to where our functions are just 0 or 1 valued. That's not a big deal. It just affects the constants. So okay, so this is the gap. So you take any g, how far off you are from the empirical average compared to the expected value is this log 1 over delta over 2m square root. This is the factor you'd get from the coin toss, plus 2 times the Rademacher complexity of your function space. So that's what we were talking about before. And similarly, now that one involves averaging over all samples of size m, but if you want the empirical one, you basically get the same result with a slight change to the constant. I don't even know if the constants were right in the textbook. Okay, so this is the one that's more practical, and it's almost the exact same result. Okay, so that's the theorem, and actually, it's not so bad to prove it from the definition.
So these can be an R, whatever.
Yeah, exactly. That's the really important, the key thing. That's right. That's right. This is the complexity of the whole function space. So it's kind of a worst case thing rather than, so there are other versions of this, but the simplest thing to do is, so So here's the deal. You can't just do it for the one function you like. So you train your function. Now you've fixed your samples. Now they're not random anymore. So you want to know, is this function going to generalize? Instead of saying the proof for just this one function I trained, let's just look at the worst case gap over all the possible functions in my space. Now some of these might have really bad loss. These are losses. It could be big, but the gap is what I care about, is that the gap is never too big over the whole class of functions. Okay, and so the proof is 4 steps. 3 of them are just unwinding the definitions, and then 1 is a bit of a calculation. Wait, is that true? Yeah. Okay, so we've got our same G. We make this definition, and it corresponds to what I said in words. You take this function, which depends on your sample S, to be the worst gap. That's what we're going to analyze. And this is just notation for the sum. Okay, so we're going to look at that function, which is the worst gap in my whole class, analyze it. If you're starting to get tired, I'm not, I feel great. We got lots of time. I'm going to write down the steps for you, and you can space out a little bit if you want. So, okay, so 1, we're going to show that it satisfies that property for the inequality I just erased, actually. And that, okay, here's where it doesn't matter if I messed up the b minus a or the b minus a squared, because that number is 1. Okay, so first we're going to show that. That allows us to apply McDermotts Inequality. I don't know if I'm pronouncing that right, which says so this is the sampling stuff. There's no Rademacher complexity there. And, okay, I don't know, we made a delta over 2 just for adding up. Okay, but now, 3, the meaning of it is that for all my G's, that's my definition. That's what I defined it to be, right? It's the worst gap you could have. But that, well, is less than this. So we just combine those. So the last thing I need to do is, where is it going to pop out? Wait, did I write something wrong here? So what are we going to show? You can guess it. We're going to show that this expectation is actually bounded by the Rademacher complexity, M of G. So those are the 4 steps. Three of them are almost immediate. Okay, that'll give us the result. So this is applying McDermotts inequality. This is interpretation of this. This is the big step. Okay? And to see this, I'm just going to argue now it's because, where's the definition? Here. We just changed S by 1 point. Each of these is an average. Okay? Averages satisfy that property, and the supremum is subadditive. It doesn't make things worse. So this holds for phi. Okay, so that's good. So all that's left is sort of a 5-line proof that, guess what? That line holds. And then we'll be able to break, probably early actually. Okay, and then we'll wrap up by showing that you can go from empirical, or the empirical versus the actual Rademacher complexity. Okay, but the main step is this one. Take a breath. I don't like doing math. Yeah, I don't actually like doing math in front of people. It's a more private thing. You know, because it's like, on the one hand, it's the way you think about it, right? You're going through it, you're thinking it your own way, but then you also have to explain it, you know. It breaks the magic, I think. It's a little voyeuristic, actually, but I'll do my best for the sake of this. What should I have done? Teaching? Yeah. I try to avoid it as much as you can ask my grad students. That's a part of the you know. You like talk. You like giving talks, right?
No, it's a private thing too.
Yeah.
I don't like the people.
Yeah, but yeah, right. So that's why I like these slide talks more. You just get. Here's what I did. It's, you know, read the paper. So. Okay. Well, here we go. I got to do 1, 2, 3, 4, 5. It's 6 lines, 7 lines basically. Okay. So here it is. We're going to try and prove that the expected value over S, we're trying to prove that is bounded by 2 times I should just ask Jeff to come up. You know this one. Come on. No, it's okay. I'll do it. All right. So here we go. So start from the definition. What is it? It's the expected value over S of the supremum G of the gap. That's the definition. Okay. Now what I'm going to do is throw in an extra expectation of a different S. So this guy right here, there's no S there. Okay? But that's the same as expected value over S prime, right, of, well, that's it, of expected value of G. So I'm going to pull this on the outside. I mean, I'm just going to combine this into 2 steps.
S prime still the one phase modification of S?
Exactly, yeah.
With a random flip or?
Just one guy, yeah. Flipping one guy at position I. And now I've kind of symmetrized the definition like this. So I've got a lot of expectations flying around, but I took something that was an expectation that didn't have a data set, and I just threw in a data set. Okay? And basically, I can take this out, because again, I'm going to use the subadditivity of supremum to say that and now it's the symmetric definition. Okay, so that's great. And now we're going to just actually write down what this is. These are averages over 2 different data sets, right? So this is, we're actually talking about the sum 1 over m of sum I equals 1 to m G. Now they're all the same. Let me put this at J, except for 1. Okay, so these all cancel out, and all I'm left with is that. Okay, so what I got is okay. So now what I'm going to do is, it doesn't change. So I had, okay, actually I kept the sum, weirdly. Sorry. Let's just write this as, sorry, this is not, sorry, I didn't change just one. They're just two completely separate draws. There's a G of Zi and a G of Zi prime. They're just two data sets. And now you make this observation that since they're symmetric, I could flip their roles and get a -1. And it shouldn't change anything because I'm just interchanging their roles. So, and I can rewrite that flipping as introducing these Rademacher variables. So that's kind of the key part. I have the two data sets, I symmetrized it, they're completely different. I'm subtracting Z and Zi prime, G of Z and G of Zi prime. But the roles, I'm taking expectations over S and S prime. So it doesn't matter if I flip it with a -1. And so I can also take expectations over these plus or -1 variables. Okay, and that, now I just multiply through, and I get 2 times the definition, 2 copies of the Rademacher complexity of G. It's over 2 different data sets. Okay, so that's actually the proof of that result. Make sense?
Wait, sorry, did you say that last part again?
Okay, so I got to here.
Is G positive?
Let me go over it. So,
P is valued in like 0, 1, right?
yeah,
0, 1.
it's 0, 1 valued, yeah. Okay, so I'll just go over it anyways. The definition of phi of S is the expectation over S, the supremum of this gap between the empirical average and the actual expectation. But the expectation is the same as the expectation over a totally different random data set. And now we pull these random data sets out and we're subtracting 2 of them. Okay, less than or equal to, because of subadditivity, this. Now we just write down what it is. It's 1 over m sum G of Zi minus G of Zi prime. Okay, now the funny thing is, because it's symmetric, I could rename these guys and I'd get the same inequality, except now these guys would be flipped. Or I could flip any pair of the same of SIs and SI primes. And so that allows me to introduce the Rademacher variable, which is +1 or -1, without changing, this is an equality, without changing the expectation. And now when you just multiply these through, you get the definition of the Rademacher complexity. Okay, so.
Is this sharp in any sense at all, or
No.
it's just the best known universal bound?
No, it's not sharp. It's just, it's a uniform bound. And there's been follow-up papers where you can talk about local Rademacher complexity around a little ball of functions around your function, but I didn't find it to be super informative. Let me just say in words rather than writing another bunch of lines. We care about, this is the one where it's averaged over all data sets of size S. How do you go from that to the empirical one? The crazy thing about it, which is kind of funny, is we're going to use McDermotts inequality again, applied to a different function, which will just pop out an extra factor here, basically. But the function we're going to apply it to is the empirical route of macro complexity. Okay? So that's kind of cool. So that's how you define that function, show it satisfies it, and just pops out an extra little log factor. I'll skip that. Oh my gosh, I'm not done. Now we have to, so we have till 10:30, I think. Anyways, I'm going to take this time to, no, we're supposed to break now. The last thing I want to do, which maybe I'll save till after the break, is to then apply the definition to SVMs and show that you get the bounds we talked about. But maybe, who's in charge of the session? Maria? Stan? Should we take the break now and then do another? Let's do that.
Just take a break.
I'll have another 10-minute calculation, and then I'll do a new set of slides. Good.